The problem says to prove that a group with two elements of order 2 that commute must have a subgroup order 4. I don't want to take the time to do a full proof of this, but let's try to get across the idea. And I think probably a full proof for a test would be a bit too much, but maybe in a brief argument, the idea of a proof, that kind of thing, showing me that you were thinking about it in the right kind of way. But it seems kind of hard. Like, okay, how in the world are you going to possibly do such a thing? We are just trying to think of ideas here. Well, certainly this subgroup, which I'll call H, has got to have E in it, the identity, which doesn't have order 2. That can't be one of the elements of order 2. The identity always has order 1. Say A and B have order 2. Assume order 2. And we are also assuming that they commute. We're assuming that AB equals BA. That's got to be relevant somehow. We need to use this information to somehow construct a subgroup of order 4. And I'm trying to say H is going to be it, but the question is, what's the last element? Well, by closure, it's got to be A times B. By closure, question mark has to be A times B. That question mark there. What else could it be, right? I mean, you could give it another name. You could call it C or something, but C would have to be A times B by closure. And that has to give you something distinct. It can't equal A, for example, because if it did equal A, we did this kind of argument before. If A times B equals A, left cancellation would imply B equals E. And if A times B equals B, right cancellation would imply A equals E. In other words, I'm trying to say A times B has got to be something new. It's got to be a fourth element. It can't be the identity either, because having order 2 means each element is its own inverse. If we assume these have order 2, that's going to mean A squared and B squared are both equal to E. In other words, A inverse equals itself and B inverse equals itself. So AB cannot equal E, because if AB did equal E, then A and B would be inverses of each other. And we're assuming that they have order 2, they're their own inverses, and they are distinct. That's a contradiction. So A times B is something new. So this set would have order 4. The question is it a subgroup? Is it closed? Does every element have an inverse in the set? We certainly know E, A, and B have inverses in the set. What about this new element A times B? Is it its own inverse? Does it have order 2? It must. Why? The assumption that the commute must be important. What would happen if we squared AB? Oh, remember last week we proved that in a abelian group, if G is abelian, then give me 2 arbitrary elements. I'm going to give them different names, C and D, say, to the nth power, that this exponent rule worked. That was something we proved last week. Well, we don't have an abelian group here, but we do have 2 elements that commute. Well, on the big group overall is not necessarily abelian. But we do have 2 elements A and B that commute. we're assuming that H is going to be an abelian subgroup, this property will work for these elements. I mean, you can, if you're unsure, you can also always do this. By definition, AB squared is that. And then because A and B commute, I can show this kind of work. Right there, I use the commutativity. That's the same as AA times BB. In other words, A squared times B squared. Okay, you wouldn't have to do that if you knew you could use this fact. And it's true when C and D commute as well. What does this give us? This gives us E times E, which gives us E. In other words, AB is its own inverse. Therefore, the inverse of AB is itself, proving that this H is closed under taking inverses. The only thing left to verify is it closed under multiplication. Let's effectively prove it with a Cayley table. Okay, so we'll fill out the Cayley table. We know what most of this looks like. E is the identity. So that part gets filled in quick. We know A, B, and A times B all have order 2, so we get a bunch of E's on the main diagonal just like before. This should feel very familiar to the D4 example. We know A times B is A times B. We know B times A is also A times B because A and B commute. BA equals AB. What about everything else here? Let's take it step by step. What about A times AB? Trying to fill in this spot right here. By the associative property, that's A squared times B, but A squared is E. This is B. What about, what goes here? What about B times AB? Again, A and B commute. Use it. So this is B squared times A. E times A is A. 2 left. Try this one next. What's AB times B? It's AB squared. AE is A. And what goes there? AB times A. Once again, A and B commute. I could write this as A squared B, EB, which is B. That effectively, those calculations verify this closed under multiplication. Not really writing it as a proof because I'm not going to explaining it. Probably be too much to write as a proof, you know, for certainly for an exam, maybe even for homework, right, to write all that out. In fact, I've already given you some flexibility on verifying closure by making Cayley tables on homework problems already. I'm assuming you're doing the calculations correctly here, should be checked. And yeah, this is analogous to the D4 example. In the D4 example, these non-cyclic subgroups are order 4. You can think of the E as being R0, the A as maybe being R180, the B being maybe H, and the other one's going to be V. Or this could be D and this could be D prime. And it would work. It would follow this kind of pattern. It would be isomorphic to this group. Anytime you have 2 elements of order 2 that commute, you can create another element, AB, such that if you create such a set, you get a non-cyclic subgroup of your given group. Which makes you wonder then, if your big group is cyclic to begin with, could this possibly happen? Could this kind of thing possibly happen in a G that's cyclic to begin with? The answer is no. In a cyclic group, you're not going to have more than 2 elements of order 2. Or you're not going to have 2 elements of order 2. You're only going to have 1 element of order 2 in any cyclic group. That's a special case of a theorem that's going to be worth remembering for us here.